All right, so now we're going to talk about graphing the derivative. So get your notes title in your notebook. And then for this first part, you can probably just chill and observe because we're going to describe how to graph the derivative and we'll get more practice tomorrow. Okay, and then I'll let you know when to take notes, but you should take notes pretty soon here. Okay, so notes, sketching derivative graphs. And remember, derivative is the same as slope, so maybe if you forgot that, put slope of tangent line is the same as the derivative. Remind yourself of that in your notebooks. All right, so let's get started. Consider the function shown, let's say below. Notice the curve at the first point, x equals 1/2. The slope of the curve here appears to be about 1. So at x equals 1/2, the slope of this tangent, this slope m equals about 1. Then at x equals 4, this slope right here, this blue slope, looks like it's about m equals 1/3, the slope of the tangent line, or the derivative. The derivatives at those points are 1 and 1/3. Can you analyze and sketch the slope graph on the grid below? Okay, so here's one way to think about sketching slope graphs. We can think about, actually I'll do it right here, we could think about making a table for the slope graph. So y'all have sketched graphs by making a table, right? I'm going to make a unique table that has x, and then it has the slope of f. So, oh, hold on, sorry, x and then f prime at x. And remember, this is the slope at x. That's what f prime of x means. So we already have a couple slope values. We know at x equals 1/2, the slope looks like it's 1. This is m equals approximately 1, right? Let's do like one a little bit before 1/2. So let's see, let's do like 1/4. What does a slope look like right here? And I will show you how I calculate that really quick. So rise over run. So here's where we go like over 1 about from this point. So it looks like we go up 1, 2 over 1. So it looks like the slope might be like 2 at x equals 1/4. So at 1/4, it looks like our slope is 2. Then at 1/2, it looks like our slope is 1. We already had that one given. Then let's do at 2.5. 2.5, what does it look like our slope is? Let's see, rise 1 over 1, 2, 3. So at 2.5, it looks like our slope is, I think it's a little bit bigger than 1 over 3. So let's say it's 1/2. Rise over, yeah, sorry, let's say it's 1/2. And then at 4, it looks like our slope is 1 over 3. It's kind of hard. We're estimating slopes. Doesn't have to be perfect. Okay, so now let's graph the slope. This is the graph of f prime, so that would be the graph of my slopes. So graphing the derivative would look like this. 1/4, and then we'll graph the slope, is 2. At 1/2, oh, sorry, 1/4 is not there. That was 1/2. 1/4, 2, 1/2, 1. 2.5, about 1/2. 4, about 1/3. Okay, it looks like our slope or our derivative graph is going to look something like this. Doesn't have to be perfect, but that was an example of how you could graph the derivative graph. Okay, so one option is to graph or to plot the slopes in a chart or in a table and then graph those slopes. Now, let's think of a more calculus-y option, and let's look at a more kind of calculus option and one that we need to actually get familiar with. Okay, so below we have the graphs f in red and f prime, the slope of f, in blue. So this is the derivative graph and the original graph. The original graph is in red, the derivative graph is in blue. I've given you the equations here if you're curious what equations they are. And we're going to make some relationships between these. We're going to make some connections. So Please fill out these tables, pause your notes for a second, and create all of these tables in your notes. They should take up like an entire page. So use this formatting, pause, and go ahead and create those tables. Okay, now we're going to fill them out. So let's go ahead and use these graphs to fill out these connections. The first connection that we need to make is what's happening when f of x is increasing. So I'm going to highlight that in green, but I'm also going to draw what increasing looks like, so we remember what increasing looks like. I want you to draw the same. And then let's highlight where f of x is increasing on our graph. So f of x is our blue or our red graph, right? F of x is increasing right here. It's going up, 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 and it stops right there, has a maximum there. It also starts decreasing, and then it starts increasing again right here and keeps increasing forever, it appears. Okay, so while f of x is increasing, in that zone, I'm going to mark that zone for the x's. I'm marking that zone on the x-axis. And then I'm going to erase my highlights on f of x increasing. Oops, I erased the wrong one. What's happening with our blue graph in that zone? So what do we notice about our blue graph in that zone? And you can make a guess. Our blue graph is positive. Our derivative graph, f prime of x is positive. Or we could write f prime of x is greater than 0. That's saying the same thing. Okay, so make that note. What about, okay, really quick, let's remind ourselves what positive and negative means. That's the x-axis, right? Positive means above the x-axis, negative means below the x-axis. That's what positive and negative means. All right, so you can see that the derivative graph is above the x-axis in that like range. Okay, let's now look at where f of x is decreasing or pointing down. And I'll do this one in blue. So f of x is decreasing. I'm going to highlight it in blue. F of x is decreasing starting here, going down, 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 and here. And make a guess. You could probably make a guess and figure out what is happening with f prime of x in that same zone, in that x zone, that region where f of x is decreasing. What's happening with the derivative graph? What's true about f prime here in this zone? F prime of x is negative. So we're going to write f prime, the derivative, is negative. And you could also say f prime of x is less than 0. Same thing. Okay, so now let's make some more connections. We need to define a critical point. So really quick in your note, critical points, like make sure that you know all of these are critical points. Relative max, relative min, saddle point, and cusps, those are all critical points. And I'm going to go ahead and look at the max to see, actually I'll tell you what's true at critical points, and then we'll look at max and mins. Okay, so at critical points, these two things are always true. F prime of x equals 0, or there's a or, f prime of x equals undefined. So now let's look at our critical points on f. So remember, we're looking at f of x first, the red graph. Let's look at our maximums. So our maximum on the red graph happens right here. And what is true about f prime, our derivative graph? And we're going to describe what changes about it. So our derivative graph equals 0 at that point, right? And that makes sense, right? Because the derivative at this point on the original graph, f prime, the slope of x equals 0, so that's why it's 0. But also, f prime of x, we could say, goes from positive, it's above the x-axis, and then at that maximum, it switches to negative. So in our little box down here, we're going to write f prime of x goes positive to negative when f of x has a maximum. And let's write underneath that f prime of x, the derivative equals 0. Those are both true. Okay, what about for minimum? What about for a minimum? So I'll do that in green here. We have a minimum on our original function, f of x, right here. What's true with your derivative graph? Well, again, the derivative at this minimum, the slope f prime of x equals 0, and that is showing up on your derivative graph. We're at y equals 0, but also we're changing, our derivative graph is changing from negative, and it's going to positive. So we're going to go down here and write f prime of x goes negative to positive, and f prime of x equals 0. That's true for minimums on f, if f has a minimum. Okay, saddle points, and actually let me draw a maximum looks like this, right? We all know that. This is the max. Minimum looks like this. We all know that. Saddle points look like this, and we do not have an example of a saddle point here. So we're just going to say f at saddle points, f prime of x does not change sign. Okay, so let's just write that note. F prime of x does not change sign. And we'll actually do more details on saddle points later. Okay, cusps. We don't have a cusp on this graph either, but cusps are those sharp points. So this would be an example of a cusp right at that point. Here's a saddle point. Okay, and the cusp, remember, you can't take the derivative at a sharp point. So f prime of x does not exist at a cusp. Sweet. Let's move on. We have a few more left. Okay, horizontal tangent lines. Horizontal tangent lines. So let's go back up to our graph. Don't we have a couple examples of horizontal tangent lines? We have this horizontal tangent line and this one. What is true when you have a horizontal tangent line? On f, f is my red, remember. What's true about my derivative graph? F prime equals 0. That's what's true. The derivative equals 0. It crosses the x-axis at those horizontal tangents. So let's go ahead and write that. Horizontal tangent, I'm going to draw an example. This is a horizontal tangent. And then we'll say f prime of x equals 0. Sweet. Vertical tangents would look like this. And we talked about this briefly yesterday. You cannot take the derivative. There is no derivative. The derivative does not exist when you get a vertical tangent line. So we would say f prime of x does not exist or equals undefined. Okay. Now let's go ahead and go to concavity. So I'm going to draw what concave up looks like. Concave up looks like this. It's like when your graph can hold water, kind of. That's how I was like taught. If you pour water on your graph, will it hold? Concave down is like this. And if you poured water on your graph, it would just run off, right? There would be no chance of it holding water. And then point of inflection is when you change concavity. So write a note. Point of inflection means you change concavity. Change concavity. And I will draw concavity. I will draw 2 examples of that. Okay, so we have, I'll do it in green. Okay, point of inflection. Say we go from concave down to concave up. So that's a point of inflection. Where you change concavity, like the spot that it flips, is a point of inflection. So I'm going to call that a POI. And then we could also change from concave up to concave down. And where the concavity flips is a point of inflection. Okay, cool. So now, and then again, this is concave down to up, just in case you were like struggling with that. That's concave up, and then it switches to concave down. All right, so now let's take some notes on what is true about the derivative when we're concave up on the original function, when f of x is concave up. So let's go and look at our graph again. Let's highlight the areas where f of x, the blue graph, is concave up. So f of x is concave, or sorry, the red graph is f of x. That was my bad. F of x looks like it's concave up right here. And then what is true about f prime, which is the blue graph? What's true about this graph that entire time? What is true? Well, I would say that f prime is increasing. This blue graph is continuing to go up. It's increasing. So we're going to go back down and say if f of x is concave up, f prime of x is increasing. And if f of x is concave down, you will find the opposite to be true. So let's just show you. F of x is concave down. It will not hold water from here to here. You will find that f prime of x is decreasing. So let's write that note. F prime is decreasing. Cool. Point of inflection. What's true at points of inflection where the graph changes, where f of x changes from concave up to concave down or vice versa? You will have a max or a min on f prime. In this case, we have a minimum. So the derivative graph, if f of x has a point of inflection, the derivative graph, f prime of x, has a max or a min. Max or min. Sweet. All right, and then let's see, I'll draw my little points of inflection here. That happens right where you switch concavity. Okay, let's go to where tangent lines are located. So really quick, what I mean is if f of x is concave up, your tangent line is going to be above or under. Tangent lines are located below f of x. All right, and under the curve. And then if f of x is concave down, your tangent line at that point is going to be above f of x. So for the tangent line approximation, or local linear approximation, that is going to be an underestimate. The calc exam will ask you oftentimes if the local linear approximation is an under or an overestimate. And it all depends on if your function is concave up or down, because you need to know, is a tangent line above or below the curve? Okay, so get the rest of those notes down, and we will now do an example, last thing, example of a graph, graphing the derivative using these things that we just wrote down, all these connections that we made. All right, here we go. Sketching derivative graphs using graphical connections. We're going to use the number lines below the graphs. So these little number lines down here to mark x values where g of x has changes related to our graphical connections. So make sure you know which graph you're looking at. Green is g of x, blue is g prime. So we have the regular graph, and then we're going to sketch the derivative graph. And we need to make some connections. So the first thing I'm going to notice on the original graph is where we have maxes and mins. So we have a minimum right here. That means we have a horizontal tangent line, right? And the derivative is going to be 0. So let me put that on my little number lines. So my number line, I'm going to put, this represents G. Actually, let's have G in green. This represents G, and then the pink is going to represent what's happening with G prime. All right, so G is, hold on. Let's put -2 on our number line. So -2. Trying to decide if I want to keep it directly above. That's fine. -2, 3. Okay, cool. So we know that at these points, G has a min and G has a max. So that means that G prime is going to equal 0 because the tangent lines are horizontal, right? Okay, and then let's go back to our graphical connections. What else is important? Where G is increasing, right? Where the original graph is increasing or decreasing. So let's mark that. So we are our original graph is decreasing from here all the way to this minimum. So we'll write the original graph is decreasing all the way from here to here. And what does that mean? If we go to our graphical connections, what does that mean about the derivative graph? That means that the derivative graph is positive. So let's go ahead and note that. So that means G is going to be positive all the way until here. And then we switch to increasing all the way into 3. So increasing. And that means, oh, sorry, decreasing means the derivative graph is negative. My bad. Negative, negative, negative. Increasing means the derivative graph is going to be positive. If we go back up, we definitely wrote those notes correctly. I just like read it backwards when I was doing the graph. Okay, so let's do it for the last section. We have, and this is supposed to be faster than doing a table and more accurate. So now we have the derivative or the original graph decreasing again. So let's go ahead and make that note. Decreasing, decreasing. So that means that G prime is again going to be negative. All right. So now we have an idea of like where G prime should be in terms of negative and positive on the graph and where it's going to equal 0. Let's go ahead and put these zeros on our G prime graph. So at x equals -2, we have G prime equaling 0. And at x equals 3, we have G prime equaling 0. Okay, now let's do another G prime comparison. And this time we're going to see, is there anything else that we can focus on? What about the concavity of G to compare it to G prime? So let's go back and write what's happening with the concavity of G. So it looks like from -5 all the way to right about, I don't know, 1/2, let's say. It's the G graph is concave up. So let's go ahead and mark this x value where it changes concavity, 1/2. Let's mark that on both graphs, so 1/2. And I'm going to mark it down here on my number line, 1/2. And G is concave up all the way until that point. So concave up. And then what do we call it when it changes from concave up to concave down? At 1/2, we have a point of inflection on the graph of G. Then we can see that it switches, the graph of G switches to concave down for the rest of the time. So we're going to write a little note. We are concave down on G. And now let's make sure we know what that means for G prime. So we're going to go back to our graphical connections. When F is concave up, we're looking here. When F is concave up, F prime is increasing. So up means the derivative is increasing, down means the derivative is decreasing. So let's make that note. G prime is increasing for concave up. G prime is decreasing for concave down. And there's one more thing we need to pay attention to, the point of inflection. What happens for G prime when there's a point of inflection? This is where we look. At points of inflection, the derivative has a max or a min. If the original function has a point of inflection, the derivative has a max or a min. So we know that G prime will have a max or min, and we're about to figure out which one it is. Okay. So now we're going to graph G prime over here. We're about to use all this information to graph G prime, and then we'll be done. So first, let's think about, okay, G prime starts negative. I'm looking over here. G prime starts negative on the far left, which means below the x-axis, and then it hits 0. Then it goes to positive, so it starts negative. It's going to start down here. It's going to hit 0, and then it goes to positive, and then it comes back to 0. So really quick, let's look. Do we have a max or a min? If it's got to come up to positive and go back to 0, we must have a maximum. So we can now circle over here G prime definitely has a maximum because we see that it starts negative, goes to positive, hits 0 again, goes back to negative. Oops. Okay, so it goes back to negative. So now we can go ahead and draw that. But where does the maximum happen? It happens at 1/2. So I'm just going to make sure that I like put the maximum at 1/2. Cool. And now let's draw G prime. It goes negative, increasing, increasing, increasing. It tells us that it's increasing over here, right? Hits the maximum and then starts decreasing. So hit the maximum, start decreasing, and then at 3, we're supposed to go back down to negative. There we go. That is the graph of the derivative. Now, I don't know what you think if you think it's like faster than graphing the individual slopes, but we've definitely got to get to a point where we can graph the derivative just like this using our graphical connections. And we also need to know all of these connections so that we can describe things for the AP exam FRQs. So it's very important to know all of these graphical connections, make sure that you have them in your notes, and it's important to be able to sketch a derivative graph using those connections. All right, y'all, that's it for today. Nice work.